Greetings once again. This is the Pencrest High School AP Physics 1 video series. This is video 7C, Newton's laws for rotational motion. Now before we look at the rotational analogy for sigma F equals ma, we have to define a couple of new quantities here. First is the rotational inertia. This is the resistance that an object has to being rotated. The rotational analogy for mass, you might describe mass as the resistance that an object has to being accelerated in a linear fashion by an applied force. The more mass it has, the harder it is to accelerate. A better term for mass would be linear inertia. Rotational inertia works in the same way. The more rotational inertia an object has, the harder it is to make it accelerate in a rotational sense. So rotational inertia means resistance to being rotated. It certainly will include the mass of the object, but just as important as the mass is how that mass is distributed relative to a particular axis of rotation. If more mass is distributed far away from the axis, the object is harder to rotate and therefore would have a higher rotational inertia. Rotational inertia has a symbol capital I. It's not a vector, and it is measured in kilograms times meters squared. The meters squared, of course, is going to be associated with how that mass is distributed. So we'll see that as more or less distance from the rotational axis. Now we got a couple different situations here. We might need to look at the rotational inertia of a particle or a point mass relative to a particular axis. The point mass has a mass m and its distance d from the rotational axis. Very simply, its rotational inertia is m times d squared. So we have a hypothetical situation here. We've got 3 point masses of mass m. One's at a distance d from the axis, the other at distance 2d, and the third at a distance 3d. First mass, easily enough, m times d squared. The second is located twice as far, so it's at a distance 2d. We then have to do m times 2d squared, or I2 equals 4 times md squared. This object, despite the fact that it has the same mass, it's twice as far away. It has 4 times as much rotational inertia because how the mass is distributed relative to the axis. The third one, of course, is m times 3d squared, so it would be 9 times as much as the first one. The other type of situation we can run across is the rotational inertia of a solid object. We're going to see various kinds. We'll see disks and rods and solid balls and hollow balls and hoops and wheels and so on. These objects rotate around a fixed axis, and their masses are distributed in such a way that their rotational inertias can be reduced to a pretty simple formula. The formulas come about through the application of integral calculus, which we don't need to worry about for the time being. The objects we see will be uniform and homogeneous. That means their density will not vary across any of their dimensions. They'll be regular geometric shapes. So the mass will be evenly and consistently distributed across the object. So we have here a table of rotational inertias. We have a hoop about a central axis that goes through the middle, I equals mr squared. We have a solid cylinder or a disk about its central axis, 1/2 mr squared. A solid sphere, 2/5 mr squared. A thin shell or a hollow ball is 2/3 mr squared. Again, in the event that you need any of these for a particular problem, they'll be supplied for you, so you certainly don't need to memorize them. Now, the second concept that we need to look at is the idea of torque. Torque is the tendency to make something want to rotate. It's the rotational analogy for force. If we apply a force at a point some distance away from a rotation axis, and that force doesn't point directly at the axis or directly away from the axis, the force will produce a torque. It'll make the object want to rotate. If we apply a force this way, this object about this axis would want to rotate in a counterclockwise fashion. So this axis of rotation is directed out of the page towards you, right? The force is applied some distance r. The force makes an angle of theta with the distance vector, or the distance r. Again, you should be able to tell that based on the direction of this force and where it's applied, it makes the object want to rotate in a counterclockwise fashion, so it would produce a positive torque. Quantitatively, the torque formula is, this is a lowercase Greek t, it's a tau, equals rf sine theta. R, of course, is the distance from the axis where the force is applied. F is the force, the magnitude of the force itself, and theta is the angle between the force and the object. Torque is measured in Newton meters. The newtons comes from the force, the meters comes from the r. Sine theta is dimensionless. Now, if we look at this beam here, it's got a bunch of forces on it. Without even worrying about the numbers or the quantitative calculation, we can see that F1 and F2 would produce counterclockwise torque. F3 would produce a clockwise or a negative torque. And if you look at F4 and F5, F5 points directly away from the rotation axis. This would not make the object want to rotate at all. F4 originates on the axis, so this also would not make the object want to rotate at all. Now, you might remember Newton's first law, sigma F equals 0. Verbally, this is the one that says an object in motion tends to stay in motion, an object at rest stays at rest, and all the rest of that. We translated it to say that when the forces on an object cancel out or balance, the object doesn't accelerate. We can say the same thing for rotational motion. Instead of force and linear acceleration, we would say torque and angular acceleration. So if sigma tau equals 0, the object will not have any angular acceleration. Sigma tau, of course, means the sum of the torque terms acting on a particular object. If they cancel, if they equal 0, then it won't accelerate. It won't rotate. Conversely, if the object doesn't have any angular acceleration, then we can conclude that the torques must also cancel. We typically call this situation equilibrium. Note that sigma tau means the sum of the torques. Each force can have a torque term associated with it. When we add them all up, they should cancel out. We're going to look at this in much more detail in the next video. So now we'll go to Newton's second law, sigma F equals ma. If the forces are unbalanced, the object will accelerate. Same principle applies for rotational motion and torque. So torque is the rotational analogy for force. Rotational inertia is the analogy for mass. And angular acceleration is the analogy for A, or linear acceleration. So it's written this way, sigma tau equals I times alpha. On your formula sheet, it's written alpha equals sigma tau over I. Same thing. Stated verbally, if the sum of the torques does not equal 0, the object will have an angular acceleration. If they don't balance, it will rotate. Sigma tau is also called the net torque, particularly when it's non-zero and the object rotates. Now, the general process here for application of either situation involves a standard free body diagram, making sure that the forces are not only in the proper direction but also in the proper location on the object. In other words, where they're applied is important. Steps look something like this. We construct a free body diagram. We know how to do that already. Just make sure that we put the forces in the right orientation and the right location. 2, we write force equations if necessary. 3, we write torque equation. This is a new idea. We then make a decision: is the object in equilibrium? If yes, we use sigma torque equals 0. We'll see this in more detail later. And if not, if it's not in equilibrium, then we use sigma tau equals I alpha. If there are multiple objects, we combine the force and torque equations and solve for whatever it is that we need. So we'll look at a sample problem. This is the modified Atwood machine. We have a disk of mass M1, radius R. It's mounted such that it has no friction. There's a string wrapped around the disk. It's connected to hanging masses M2 and M3. M3 is the bigger of the two. The string doesn't slip on the disk. So before we do the free body diagram, your common sense will tell you something about what's going to happen here. M3, because it's heavier, M3 is going to accelerate down. M2 is going to accelerate up. And the disk will rotate in a clockwise direction. So first, here's our free body diagrams. The disk is being held up by some force Fn. We have M2 and M3 with their associated gravitational forces. And then we have an Ft3 pulling up on M3. That same Ft is pulling down on the side of the disk. On this side we have M2G. We have Ft2 pulling up and Ft2 pulling down on that side of the pulley. Now the pulley doesn't accelerate in a linear fashion, so its force equation is irrelevant. What's going to matter is its torque equation. Now, you might remember that we said earlier when we looked at Atwood machines that the tension is the same everywhere in a string. We have to revise that for the modified Atwood machine because we need to have a different torque. We need to have a net torque on this disk to make it rotate, which means that the tensions on either side of the pulley can't be the same. If they were the same, then the pulley wouldn't rotate. We know that the pulley is going to rotate in a clockwise direction here, so we'll see that Ft3 has to be greater than Ft2. So what we will need is a linear force equation for each mass and a torque equation for the pulley. First we'll look at the force equations. Nothing new here. M3 moves downward, so Fg3 is positive. Ft3 for the mass is negative, equals M3A. That's this one, accelerating downward. For M2, Ft2 pulls up, minus Fg2 pulls down, equals M2A. And the torque equation, this is the new part. We pick the center of the pulley, that's the rotation axis, it's going to spin around the middle. And recall that the torque is R times F times sine theta. Well, the R is how far away from the axis the force is applied. So we have the radius of the pulley R times Ft3. Can you see why the sine theta can disappear? This is tangent to the circle, tangent to the edge of the disk. So in other words, the angle between the force and the radius is 90 degrees. Sine of 90 is 1, so we can eliminate it. Notice that the object is rotating clockwise, so we make that the positive direction. Therefore, this R times Ft3 is positive torque. R times Ft2 is negative torque, equals I times alpha. So this is the torque equation for the disk. Again, note that the direction of the motion is the positive direction. We've established clockwise is positive because the disk will accelerate in that direction. Okay? We already talked about the tension on each side. In order to produce a net torque on the disk, the tensions on either side have to be different. Again, the string is tangent to the surface of the disk, so the angle between R and the FTs must be 90, so that sine 90 can go away. We're going to replace I in the torque equation with the expression for a disk, which is 1/2 mr squared. We're going to replace alpha with A over R. Recall that from the rotational kinematics, the tangential acceleration of the edge of the object is equal to alpha times R. So we're going to replace alpha with A over R. Here it is. R times ft3 minus R times ft2 equals I times alpha. We can eliminate this R with one of these, and then these R's with the one that remains, and we end up with ft3 minus ft2 equals 1/2 m1a when we eliminate some of the R terms. So now we have three equations. We can combine them to eliminate the ft terms. This one eliminates that one. ft2's go away, and we end up with fg3 minus fg2 equals 1/2 m1a plus m3a plus m2a. And then we can generate a relatively simple expression for the acceleration of this system. We can then solve for A and put it back into the force equations to get the two FTs. Again, that modified Atwood machine is a popular type of problem. All right, so that's it for Newton's second law. Sigma tau equals I times alpha. Next up is torque equilibrium. Until then, enjoy. See you again soon.